To present today with the talk entitled Perspectives on the Application of Information Theory in Quantum Science. Dr. Robin Sakar is a distinguished professor and researcher in the Department of Chemistry at UAM Iztapalapa. He holds the position of Professor C in the field of quantum chemistry since 1996. Dr. Sakar is also a member of the National System of Researchers with the designation of National Researcher Level 3. He completed his bachelor's degree at Queen's University in Kingston, Canada, and obtained his master's degree and his PhD from the same university. Between 1986 and 1988, he conducted research at the Universidade Federal de Pernambuco in Recife, Brazil. Additionally, he is part of the advisory editorial board of the Quantum Reports Journal. Dr. Sakar's research focuses on the behavior of quantum systems. His work involves reduced density matrices and their application in information theory for a better understanding of chemical systems. In particular, he analyzes the effects of electronic correlation and quantum correlation in chemical systems. He actively contributes to the development of numerical methods in computational chemistry and physics. And from my own experience, I can tell that he's an excellent teacher. And without further ado, I leave you with Dr. Robin Sakar.
Thank you. Thank you. Thank you, Azel. Thank you very much for that introduction. And I would like to, first of all, thank the organizers of this event for the invitation to share with you this afternoon some of the things that we have been working on, and also for you in the audience. Thank you for your presence. Just a little bit of history. Hazel said a little bit earlier, I did all my education, undergraduate and graduate education at Queen's University. I would like to share something with you. Queen's University is well, not, I don't know if it's famous or infamous because it's where Elon Musk first went to university. So I don't know if it's a good thing or if it's a bad thing to say that Elon Musk went. And I think he was at the same time, I never met him, but we were there more or less in the early 90s. I think I finished my PhD in 94. And I think he was more or less an undergraduate around at the same time there at Queen's. So that's one thing. Okay. So let me, I'm Robin Sakar, Department of Chemistry. Here is our logotypo, right, for Department of Chemistry. And what I'd like to share with you today is perspectives on the applications of information theory in quantum science, okay? Now, something is missing from this title. Okay, really, it should be quantum science and technology. Now, I understand we're a very varied group here. We come from the natural sciences, and I would hope that there's some engineers in the crowd here listening, because really, what the emphasis is on is to use the phenomena that we have in quantum mechanics and quantum science, but more important, to apply it, okay, to make technology. This is what everybody is interested in. Now, I won't be speaking about technology, okay, because I don't work in that area, but this is just what the emphasis is, quantum science and technology. And now there are various initiatives around in the world. All the major the developed countries are really focusing on this. They have announced initiatives that they really want to have that quantum science and technology will have an impact in the future. And I was reading a little ways ago, the world we live in right now is, one of the characteristics is that there is a lot of competition between the United States and China, okay? And both of these countries have announced, and this isn't recent, this has been years back, they've announced they're willing to really heavily invest in the development of quantum science and technology. And what has happened is that what we're seeing is that China is investing a lot more in the development of quantum science and technology than the United States. So if we can take that as a measure of what will happen in the future, I think in the future we can expect to see more quantum technology coming out of China. Okay? See? So I just wanted to share that with you. So really it should be quantum science and technology because it's the application of quantum science to make stuff. Okay? Information theory. Now, let me speak information theory. Information theory has been with us now, I think, for going on 70 years, more or less, since the work of Shannon. And I don't think it can be overestimated the impact that information theory has had on the society. The way the internet operates today, we all use the internet. The way the internet operates today is based on information theory because what Shannon was able to do is that was able to formulate mathematically what information is, a mathematical theory of information. And he did this thinking of applications because in communications, wanted to see how things could communicate. And since then, this work has permeated to various fields. I think it's very difficult to think of a field which information theory has not touched. And of course, one of the areas that information theory has touched is quantum theory. Okay? So this is what I would like people to take away. Information theory and quantum science and technology. Okay? Perspectives, particular my own perspective on how it was developed or what are the things that and I'm a quantum chemist, okay, what we are interested in, and hopefully at the end we'll be able to see, we understand where we started, and then we're going to see where we're going, okay? So just let me, this is what. Now I just wanted to, everybody here, I just have a question, okay? So I'm going to be receiving questions at the end, but I would like the question, no? So everybody here, what is the significance behind our logotype? What does that mean? We have the UAM, right? We're WAM-E here. But what you see is these three letters, UAM. What you see here, they're not separated, are they? No? They're not separated. They're intertwined, okay? Another word that one can use and what the founders of the university now 50 years ago, what they said, right, is these are, the letters are intertwined, right? They're entangled. And what does that mean? It means what they wanted to, what the founders of the university wanted to show, that the thought or what they wanted to build was that they wanted to build science based, well, not only science, but the three divisions based on interdisciplinary work and interdisciplinary thought, right? Because what we think is that whatever the scientific problem is, we can get clearer and better and different perspectives on the problem if we look at it from different points of view. And this is what your university, our university, that's what our logotype means, right? Okay? All the three pillars, if you want, the science, humanities, biological sciences, natural sciences, and engineering, right? you shouldn't look at them as being separate entities because all knowledge is intertwined. You know, and I think this is a very important thing. And why I wanted to state this is because that it will it will understand, we can understand a little bit better where I'm coming from now. And now this is the only slide that's in Spanish, okay? So the rest of it is going to be in English, okay? Now, what this shows is just a diagram. Usually these diagrams, these Venn diagrams, right? They like to show how different elements interact with one another. And what we have here is that we see that quantum chemistry, okay, is at the intersection of chemistry, physics, mathematics, and computation. This is what I'm a quantum chemist. These are our roots. Somebody once said, I can't remember well, in order to understand where we're going, we have to know where we're coming from. Because if we don't know where we're coming from, we won't know where we're trying to go. And this is what quantum chemistry is at the intersection. Also, you have things of physics, chemistry, computation, and mathematics. And just a little bit, I just want to plant a little bit of seed, a little seed in your mind here. Why is it like this? Well, quantum chemistry, the way that quantum chemistry started, they were really, the quantum chemist is a cousin, a brother, or definitely related to what is the atomic molecular physics. What is an atomic and molecular physicist? Now, back when quantum mechanics started, which is now over 100 years, the theoretical physicists were studying atoms and molecules. This is what they were doing at that time, okay? So we have a relation here between the atomic and molecular physicists, right? But now, why computation? Because only for very simple systems, one electron systems, in quantum chemistry, that we have exact solutions. We don't have, and this is the beauty, I think, of what we do in quantum chemistry. We don't have exact solutions, but that doesn't mean that we say, well, we don't have, so we're going to say goodbye. No, that's it. No, what we can do is try to approximate things and do very, very good approximations to try to understand what it is that we are, the nature of matter that we're trying to study. Okay, so that's important. Approximate methods. So one of the things in quantum chemistry that people try to analyze, how good, they always ask this question, how good is the approximation? If you go to a quantum chemistry symposium, always, how is your method? What are you doing? What is your basis set? No, etc. Because you want to know, well, really, how good is the approximation? And this will be important for us to see how we entered this, okay? And of course, since these methods are approximate, okay, they have to use algorithms. So algorithms, this is where the computers come in, okay? So this is a very simplified idea of what quantum chemistry is, because now, this is when it started, but now there should be another circle for material science, how there's interaction with material science, because over the years, people are not just interested in just atoms and molecules. You can go to solids, bigger structures, because the need is you want to understand why more complex materials, why they have certain properties. Okay? If I'm going too quickly, just let me know. It feels really strange speaking to you in English. I'm accustomed in Spanish, okay? So let me go, no? So what is the outline? I'm going to talk about some historical perspectives, motivations. The motivations for us were uncertainty relations. Then I'm going to go on to talk about the tools that we use in information theory, which are information entropies, and how you can use information entropies to build what are the correlation measures, okay? And then after that, I just like to speak in general about applications because, okay, well, people are interested in this, but how are they applying all these ideas? How are they applying it to in different in fields of science? Okay, I just coming over here, uncertainty relations. Coming over here, I saw a poster. You know, in WAM, we now have a new model of learning. No, everybody, right? It's called MACA. MACA, right? One of the focus of MACA, and it says right there, right? We have to learn how to deal with uncertainty. We have to learn how to deal with uncertainty. It doesn't. What I'd like to do now is try to relate that a little bit with what we see when we're talking about uncertainty relations, okay? So first, uncertainty relations, just a little bit about uncertainty relations, right? Here we have uncertainty relation. This delta, well, for people in physics, chemistry, yeah, this will be, everybody, you know, this is familiar, okay? But what are these deltas? These are standard deviations, okay? So what it's telling us, okay, is that there's a, and this was due to Heisenberg, there's an uncertainty principle here, and now the physicist will say, well, this is telling you that the two operators don't commute. No? Well, that is the mathematical language. But what does it mean? We're trying to understand what does it give us? And what it really, I can try to make an analogy, it's telling us about the limits we have on our knowledge, on our ability. So let me give you an idea. All of you, I think, here are in postgraduate work, right? Sooner or later, you will have to write a thesis, okay? Maybe you'll have to write a paper, okay? Now, you're sitting there trying to write a paper. You have this idea, okay? But what you do is that now you have to express this idea, okay? And we all know that sometimes that is not the most easiest way. That is not the most easiest thing to do, okay? And not only that, it depends if you do it in Spanish, if you do it in English, if you do it in another language. So you have this abstraction, and we're trying, okay, you're trying to express something, but there is a limit. And what is the limit is because you are choosing a representation. You are choosing the language, and every language has its own limits, has its own strength, has its own weaknesses. Okay? You might be able to do something very well in Spanish. Maybe when you try it in English, it doesn't work so well, right? So there is a limit. And this is all about communication. Communication. After information theory was introduced to understand how you could communicate by signals, it has been applied in the study of languages to understand why languages form, what is the mathematical basis behind different languages, okay? So what does the uncertainty principle tell us? It's telling us is that there is a limit to that, okay? Now, everybody says in the textbooks, that is the Heisenberg uncertainty principle. So you could maybe think, well, yeah, Heisenberg did that, right? But in the original paper, Heisenberg never spoke about standard deviations. It was all about uncertainty. It was after when Kennard and Robertson, they were the ones that, well, this is about uncertainty, let's use the standard deviation. So this, what you see in textbooks, is really due to Kennard and Robertson, okay? So it's uncertainty, okay? Uncertainty, probability distributions. Quantum mechanics, at its heart, statistical. We'll get that a little bit later. The interpretations, because quantum mechanics a couple years ago completed 100 years. Even in the newspapers, the major newspapers I was reading, there were criticisms. Everybody knows quantum mechanics works. We have spectroscopy. 2 years ago, Nobel Prize in Physics was awarded to the people who did the experiments to show non-local behavior. It's a reality. But what does it mean? Meaning. And actually, it was a strong criticism because since then, what does it mean? So hopefully, we'll get there. We're on the journey, we'll get there, okay? Okay, so Kennard Robertson in terms of standard deviations. But when you look at a standard deviation to try to measure what is the uncertainty in a distribution, and like Maka says, we have to train ourselves to become accustomed to uncertainty, right? So standard deviation is not the best. Standard deviation is based on a Gaussian distribution, normal distribution, okay? And many quantum systems don't have that kind of distribution, so it's not that best. So in 1975, around what happened was that in these works, these original works, 75, there's a review article. I think there's another one in Reviews of Modern Physics, but I haven't put it here. Now, what you can do is that you can use these Shannon entropies to quantify the uncertainty. Because what the uncertainty is, remember, the uncertainty in measuring the position and measuring the momentum. Okay? Then, so you can formulate it, and there are certain benefits, okay, to formulate the uncertainty relations in terms of entropies. Okay. So these are the definitions, okay? Now, there are just some things I'd like. Now, these are the squared norms, okay, of the wave functions in X or in P. And what you see is that these are integrals, okay? If you're dealing with discrete data, you don't have integrals, you have sums, okay? But because we are working in what is called continuous variable quantum systems, we're not looking at spins, okay? This is one aspect of quantum science and quantum technology. If in the hunt for the quantum computer is that you look at discrete systems, so then you have summations. Here we have integrals, okay? So you have the wave function in X, in position, and we have the wave function in P. So now why is it? Because in the Schrodinger equation, okay, there's a Schrodinger equation, okay? What you get from the Schrodinger equation, you can get the energy, but you can also get the wave function. The first, when quantum mechanics was developed, you guys, if you took your undergraduate here, you will have taken the structure of matter. That is the course here in WAMI in chemistry, and you see there, because why solving the Schrodinger equation, you can get the different energy levels, right? And we all know that it is correct because you can do spectroscopy, and with spectroscopy you can see transition from one level to another. So the focus on the energy, okay? But also solving this Schrodinger equation, you can get the wave function. So what this is about, okay, is now analyzing the properties of the wave function using information theory. We want to see what information the wave function has, okay, to be able to understand why the system behaves in a certain manner. Now, we don't use the wave function, we use the squared norm, right? Because we have the Born interpretation. Right? How many saw the movie Oppenheimer. Ah, everybody saw Oppenheimer. Yeah. Well, just to remember, I think Born was mentioned in the movie because I think Born was the PhD advisor of Oppenheimer. And for the quantum chemists in the crowd, we know when we're treating molecules, we use an approximation where the nuclei are fixed so we can calculate electronic wave functions. And this approximation is known as the Born-Oppenheimer approximation. Now, well, this is where Born, okay? So we're still with this Born, is that, right? The squared norm of the wave function is the probability. Probabilities, we're dealing with probabilities. So one aspect of this work is very, very simple. There is still, like I mentioned, very vigorous debate. What does quantum mechanics, what does it tell us? How can you interpret it? What? So this discussion goes on. What you can do is say, well, I accept the probabilistic interpretation. I accept this, the Born interpretation. So what I'm dealing with are probabilities. So what I'm going to try to do is I'm going to try to understand what these probabilities are telling us, what they're giving us about the system that we're trying to study. Okay? So how do we go about using probabilities? Well, who studies probabilities? Well, the mathematicians, in statistics, they study probabilities, right? Very related. People in information theory, they study this. So why don't we apply information theory to study these probabilities? Okay, so this is where the direction where it goes, right? So these Shannon entropies are measures of uncertainty in the underlying distribution. So what you see, when you get smaller values, we're talking about a decreased uncertainty. And when you get larger values, you're talking about increased uncertainty, right? Another name for uncertainty is localization. We see localization, or the other part, delocalization, in many aspects in science. People in chemistry, when we see a benzene ring, what do we say in a benzene ring? We say that pi electrons are delocalized over the ring. One example. Localization also occurs when you have interference between waves. Not only in quantum mechanics, you have classical waves, right? People have known this, and they have observed quantum effects when these waves, because after all, in quantum mechanics, we have this wave-particle duality. So if we can measure this, it gives us some idea about how the system is behaving, okay? So let me go here. Just to give an idea what people are doing, Shannon entropies are not the only measures of uncertainty. Now, I don't know if there's anybody in mathematics here. This is a field because the mathematicians and the people in statistics, they're working. What are other measures of uncertainty? We're just not limited because for example, I've just put two here. Rényi. Now, what Rényi entropy does is that it introduces a family of measures with a parameter, which is this alpha. And what happens is that as this parameter goes to 1, this expression collapses to the Rényi, to the Shannon entropy. So from this point of view, you can see Shannon entropy, when Shannon introduced these measures, it is just one particular member of a more general family of measures. So people are interested in applying Rényi entropies. Salice entropy, this came from statistical physics. Right? This was introduced in statistical physics. Similar in appearance, it has this parameter. These are not the only ones. There are Fisher, another one that's called Fisher information. But not to confuse this, there are many, many measures of uncertainty. Okay? So these form the basis for complexity measures, but that's another story that I won't speak about today. And also, you might ask, well, we saw the uncertainty relations in one here in terms of standard deviations and in terms of Shannon entropies. And I can answer the question is, yeah, there are formulations of the uncertainty principle in terms of Renyi entropies. So from a mathematical point of view, what are these measures? What do they tell us? Can you say that one is better than another for what your problem at hand? Okay. Okay. So these are some open questions. What is the appropriate measure to capture uncertainties? And we're interested in quantum uncertainties. Okay. What do quantum uncertainties tell us about the system? Right. Maka is telling you have to accustom yourself to deal with uncertainties, right? Okay, okay. So, but what do quantum uncertainties tell us about the system? The idea is that information is encoded in the wave function, and now the problem is how are we going to extract this information? Okay. When we speak about uncertainty relations, I'm just going to change a little bit. Really, we're speaking about position momentum correlation between position and between the momentum. Okay. Now, there's an article when Heisenberg first did wrote his article on the uncertainty principle. There's another one that appeared from Schrodinger. And he formulated it in terms of a quantity that's called the covariance between the position and the momentum. And the covariance is a measure of statistical correlation between x and p. So we know that the uncertainty relation is somewhere there. It's telling us something about position momentum correlations. But what we need to do is how to measure this. Okay? So let me just give you a historical context of why, as a quantum chemist, one would become interested in this. Okay? First paper, more or less, one of the first, can't really say it's the first, about 1985, okay, in this article, where there was a study in neutral atoms and I think the oscillator systems, and I think those were the atoms, neutral atoms, and oscillators. That's what this work was done. Okay. So why the interest at that time? Because there's interest in electronic densities. Okay. These things, densities, probability densities. Okay. You can measure these in chemistry. You can measure now. Crystallography, okay, gives us maps of what these electron densities are. So the nice thing about it is that these densities are experimentally accessible. And there are theories. I see some quantum chemists in the crowd. Quantum theory of atoms in molecules. These are theories that have been used and are very much in use today to try to understand, for example, chemical bonding, weak interactions. Even now, what they're doing is that they're applying this theory to understand experimental densities that you measure in the laboratory, and then you can apply these methods to study. Okay. Density functional theory, which has been with us for a while, and I think this is really the impulse for this, because this is a density functional group where this paper came from, right? So now these are electron densities, but when we think about crystallography, we're thinking about you get a spatial map, in space of what the density is for different types of materials. Okay, but what about the other? What about the momentum? And there are there are, the good news is that there are experiments where you can actually measure what the momentum densities of a system are, right? These are, it's E2E spectroscopy. This is just one of them, but there are others. So the important point here is that why this started, because people had access to experimental methods, okay? Okay. Now, let's see some relations between entropies and physical concepts, okay? One, it was proposed that the entropy sum is a measure of basis set quality. I won't get into this very much, but in the quantum chemists, we all know that we have to choose a basis. That's very important in the calculation. And how we can select a good basis is very important for us, right? So this is important. It's a measure of correlation in atomic systems. Now, that doesn't seem very, how is it? We're going to get into this a little bit later on. How can you associate entropy and entropy sums with correlation? Correlation, because when we're speaking about correlation, we're speaking about two or more variables. These densities so far that we have looked at just have one variable. They're just one electron densities, okay? But we're going to get into that a little bit later on. Stopping power measurements, okay, there's something called the mean excitation energy, which comes out of something called the local plasma approximation, and the Shannon entropy comes out of these measurements. So in theory, there are experiments where we can access these, okay? Just very quickly, discrete Shannon entropy, okay, it's been proposed as a measure of electron correlation. So what you have these NIs here are occupation numbers, and these occupation numbers are eigenvalues of what is called the one matrix. Now this is a density matrix. I haven't spoken about that. How you need to change the information theory in order to treat quantum systems. But we'll get to that in a little bit when we're speaking about density matrices. So this is a proposal that correlation, electron correlation, and of course the quantum chemist is really interested in this because, like I said, from every calculation, he or she wants to know how good is the wave function that they're obtaining using approximate methods. And electron correlation is because when we have particles or electrons interacting with Coulomb via Coulomb potentials, okay, we don't know how to separate that problem, okay? That is why we have to use approximate methods, okay? Okay, so extensions, okay? This work all started out because of the interest in density functional theory, but density functional theory is based on one particle reduced density. Now, what is a reduced density? One of the beautiful things between density functional theory is that everything is reduced onto one particle. If you can imagine, what happens is that if you are solving the Schrodinger equation, for larger and larger systems, the dimensionality of the wave function increases. So when you have if you have a wave function that lives in a space of hundreds of dimensions, what does that mean? How can you interpret that? So the beauty of density functional theory is that it reduces everything on just the one electron. Now, of course, these reductions, there is a price to be paid, and what is the price? Is that nobody has found what the exact functional is in density functional theory. Okay, but that's another subject matter. Now, if you have a two-particle wave function, you can define a two-particle pair density. Now, what can you do with a two-particle pair density here in the system? You can define something that is called the mutual information. And what is the mutual information? Okay, it's a statistical measure of correlation between the variables you're studying. So what you can do is you can examine how correlation is in the system. What is the correlation between one particle and the other? What is the correlation between their positions? And you can also do this in momentum space. What is the correlation between their positions, and what is the correlations between their moment? Okay? So when we speak about statistical correlations, okay, we have interaction between particles. Now, a consequence of the interaction between particles will give us the statistical correlation, but also there's wave function symmetry that's involved. Okay? Now, this has been a topic of statistical correlations, has been a topic since Wigner Seitz, they introduced this in the 30s, and throughout the years, people have been returning to it, okay? And what was done in the past is that they looked at the correlation coefficient, because the correlation coefficient in statistics, the measure of how things are correlated, okay? Now, just to emphasize, this is a different aspect from the correlation energy, because in quantum chemistry, what we have used is correlation energy. What statistical correlation does, it takes away, or doesn't, it neglects what is the difference in the energy and looks at what is the correlation in the wave function via the densities. Okay? That is the difference, okay? So the correlation coefficient we have here, but mutual information is a more general measure of correlation because it's able to detect nonlinear correlations, okay? Now, mutual information, as you can, Shannon entropies, where you use it, there's a universe of different fields that is using it. Same here with the mutual information, right? Just not used here, but it's used in many, also used in discrete systems. I will get to a more, in a slide later on, I will come back to this idea, okay? So what we have, uncertainty measured by entropy, statistical correlation related to uncertainty, and we have the mutual information. So this forms kind of a circle in how we can go about stuff. So with these measures, what are the best measures to quantify correlations and uncertainties? This is one of we want to know when we're dealing with this, right? But why is this put down here? Is that if somebody came in and they read this slide, they don't know this is about quantum mechanics, you would think this question here comes from data science. Because in data science, you're trying to do the same things. You're trying to look at how do you measure uncertainties, and more importantly, how do you measure correlations? So there is a very, very strong analogy between what our people are trying to do here in this field with quantum mechanics and what people are interested in doing in data science. And yes, there is overlap, okay? Okay, so let me go back again to position momentum correlations. When in quantum information theory, when it started, okay, you look at Shannon, and Shannon is all in terms of densities, because this is what you have to work with, densities. But when you go to quantum mechanics, you can generalize a density to what is called a density matrix. Really, maybe I should have used the word operator here, because whenever you use density matrix, well, where's the matrix? I want to see the elements of the matrix, and there's no elements because it's continuous, right? Okay, so maybe density operator, but there's a little bit of confusion, but more or less it's saying the same thing, right? So we go to a density matrix. So what you can do is that you can formulate this using a phase space Wigner function. Wigner did this. He introduced this. This was a while back. And this is, now, the density matrix is in terms of this, in terms of the wave function, right? These are pure states. In terms of the wave function, evaluated these points, right? So you can get something that is called a Wigner function that you can say, well, this represents a probability. But let's take a closer look at this, right? If this is the probability, what you're saying is that there's a probability of finding the particle with this position and this momentum. So then the question is, where is the Heisenberg uncertainty principle? How can you do that, right? And the answer to that is that, of course, you can't do that, right? So what happens is that this function has been introduced, but people say it's not a probability function. It's a quasi-probability function, right? And why is it a quasi-probability function? Is because this function, and I'll show some, next slide will show you some pictures. This function can be negative. So now that's kind of strange, because how could a probability be negative? No? Because probabilities comes from the axioms from Kolmogorov. And one of the axioms is that it's got to be positive. So what has happened since Wigner introduced this? That there are different schools of thought. Some people from the initial, listen, this can be negative. So there's no, you shouldn't study. There's no need to examine this because right away it violates what it is, what's to be a probability. So forget about it. There are other schools of thought say, no, the negative regions is where quantum behavior is being exhibited in this function. So it is interesting and it is important to study this function, okay? So there we have. Just a quick anecdote. I think I read somewhere, somebody asked once Feynman, Richard Feynman, what he thought about negative probabilities. And the answer was, I don't see any problem. And they asked, well, why? Well, you could have a bank account that is negative. So you just move your where you are. And that's true, because bank accounts can be negative. You have debts. So this discussion continues. Okay, the Wigner function, okay? Now, what people have done say, well, no, we don't like this negativity and the problems with interpretation in terms of negative probabilities. What does a negative probability mean? Probabilities are bounded by zero. Zero, it doesn't happen, the event doesn't happen, and it's got to be above that. What is a negative probability? Other functions have been introduced. Among them, the Husimi function. So what the Husimi function does is that really it's just like a Gaussian filter. And what it does, it filters the information that you have in the Wigner function and you make it all positive. So then again, there are strong points and there's some weak points because people say, well, you're washing all the important information away at the expense of having something that is positive, okay? So these are the schools of thought. It's been used, I mean, people are using, and I'll speak a little bit about that, where they're using this now. Let me just go ahead. There, you see, these are some images that are taken from this article. Saul is sitting right there, right? Now, what we have in this first row are Wigner function. This is just the harmonic oscillator. You got the ground state, and then you got some excited states. And the same ground state and excited states you have of the Husimi function here. So in the ground state, no problem. Everything positive, okay? But when you go to the excited state, I think if I remember correctly, this might be the first excited and then the third or something, but these are excited states. What you see here in this dark shadow is that the Wigner function here, which is on this, it's negative, right? The Wigner function here is negative. Here, it's negative, okay? Q-simi function, on the other hand, it's not negative, okay? It's positive definite here, so very nice. But on the other hand, what happens? You can see, if you just focus here, all that interesting structure here, which is the nodal structure in the wave function, which you see here, these valleys and ridges here. When you go to the Q-simi function, that's all lost. That's all lost. See? So this debate continues. People are using Wigner functions, okay? Using Q-simi functions. And now where are they using this? Just to give you an idea. Thermal states. Thermal states these days are very interesting because why? Let's go back in history. Thermodynamics, okay? Impulse for thermodynamics, because people wanted to know how to build steam engines. So you had all this development with thermodynamics, okay? Try to understand. Today, people are trying to construct what is called quantum thermodynamics. Because what do they want to do? They want to build quantum machines. Okay? So quantum thermodynamics, people are using these, the Wigner function, Q-simi functions, right? With that goal in mind. Build quantum thermodynamics so that people can use this to build quantum machines, okay? Okay, just go on. So why is the Wigner function attractive, okay? Because the marginals in statistics, when you integrate over one of the variables, the marginals are the position space density and the momentum space density. When you use the Q-simi function, you don't have this relation, okay? So what does this permit you to do with the Wigner function? What it permits you to do is define a statistical correlation between the x and the p variable in this way. And what comes out of it is what is put in red here. And what is this? This is the uncertainty relationship. The uncertainty relationship that we saw some slides ago. So the formulation in terms of the Wigner function with mutual information yields the uncertainty relationship of the entropic sum, but you have one quantity, and this is the price that you have to pay. Since the Wigner function can be negative, okay, the entropy of this Wigner function is complex value. So what you're getting, okay, for the correlation between x and p is not a real valued number, it's a complex. Okay? Okay? So let's go to applications. How are these tools useful? How are they being used? Because this is what we see. Well, why is there interest in all this? Confined quantum systems. There are various groups in chemistry, in physics, that work with confined quantum systems. Now, what are confined quantum systems? Well, it's when everybody who has studied quantum mechanics first model particle in a box. You know, you have these walls, right, where you're limiting the particle to be, and these walls can be infinitely high, or you can drop them. Okay, you can also confine particles by applying potentials. Okay, now, what is the significance of this? I think everybody has heard or should quantum dots. Quantum dots. I think the Nobel Prize in chemistry, I think in last year, was done for fabrication of quantum dots. And quantum dots is not a quantum dream, no. they're using this in technology. Flat screens, they use quantum dot technology in the computer or television screens. They use quantum dot technology for the image. So these things have permeated from the lab, and people are using them in the industry. Okay, so confined quantum system. What do people are interested in? How does the system react to confinement? Entropies. Okay, can entropies be used to tailor quantum control? Because what you need at the end, you want to be able to control a quantum system. How does particle interaction in confined systems influence the behavior? And there are groups, I think there's one group here, from physics. They recently had an article that was about the confined helium atom. Helium, of course, is a simple atom, but it's got 2 electrons. So what happens when you confine that, and what are the different characteristics? The emphasis, of course, and for those who have talked, we learn in structure of matter, your electrons in 1s, they have the lowest energy. You go 2s, right? 2p, and then you continue on, okay? And there's this ordering. People have been interested in confined systems because we find when you confine this, there's inversion of order. You can actually have lower lying orbitals, right, when the system is free, that are now, you invert the order. And you can think of doing engineering to take advantage of these phenomena. And this is what people have done, okay? Now, the next step is, okay, well, this is the focus on the energy. What is the information in the wave function? And how can we do this? Can we manipulate the system, okay? And what are the properties that we can get out of this, okay? Okay. Can particle interaction be used as a resource in quantum control? Well, quantum machines, we've spoken a little bit about this before. Can the Heisenberg uncertainty principle be used as a resource to design quantum devices? Open questions here. Hopefully some of you will answer these in the coming years, okay? Bose-Einstein condensates. Okay, now, what are Bose-Einstein condensates? Are a new phase of material. What we learn in chemistry, in structure of matter, you can put 2 electrons in one orbital, but when the third one comes along, it won't go there, right? So why is that? That's because electrons are fermions. But when you have particles that are bosons, it doesn't matter. You can put as many of them in there as you like. So people have known, I think they've won, this was a while back that they won for the experiments, they won Nobel Prize in Physics to the experiments to show Bose-Einstein condensation, because this was an idea theoretical that was many years before that, but finally they did the experiments and that was that, okay? So what people are doing here is that they're using these entropies to study and characterize the behavior of Bose-Einstein condensates beyond the mean field approximations, okay? They want to go, okay, what happens when these bosons interact strongly with one another? And what they see is that, yeah, when they react strongly to one another, you can actually make them behave like they're fermions. Okay? They try to separate one another. They feel kind of a repulsion because of this interaction. So people are using entropies in this way to try to understand. Okay? Density functional theory. Okay, go back. They're using these information measures to design kinetic energy functionals in density functional theory. This is one of the things that are where the idea is, because density functional theory is based on the density, but really what you need in order to calculate the kinetic energies, you need the one matrix. But what are the approximations that you can get from these information? Right? Approximate wave functions, how to get approximate wave functions. I didn't define what are these Kullback-Leibler distances, but just to give an idea and try to tie it in with what is going on with artificial machine learning. What we try, we have data, okay, and we try to fit it to some kind of model. And usually what we do is we do least squares, you know, various reasons, but we use least squares fitting, and we can get an idea of, well, how well does data, how well do the data fit to a model? Now, what people are realizing is that you can use these measures. One of them is the Kullback-Leibler distances, okay? You can use that to fit data. And in some instances, using the Kullback-Leibler measure will give you better results than doing least squares fitting, okay? So this is another tie between these ideas and what you see in data science, okay? Higher order statistical correlations. Now, usually when we think about correlations, we think about one variable between another. We think about one particle with another particle. But it doesn't have to stop there. What we can do is try to think what is happening between three particles as a group. And how does that phenomena, how is that different from when two particles are interacting by themselves? These are called higher order, no? Now, what do higher order correlations tell us about interactions in quantum systems? This is related with the idea of what is called emergent order. Now, what is emergent order? Is that there is a certain order depending on where the scale is. You can think cosmology. You have structures there that you build your systems with. Okay. Now, the relations there that you find up there at that scale, okay, will be different when you reduce and you go to a lower level. But all these different phenomena are caused by interactions that you have at each level. Okay? This idea, emergent order, one of the guys is the Philip Anderson. He passed away a couple of years ago. He's a Nobel Prize condensed matter theorist, okay? One of the authors of these ideas of emergent order. Okay? And the thing about it is that when you have more, whatever you're talking about, more particles, more whatever you have, the system has to behave differently because you have more. I recommend, if you haven't, there is an article that I absolutely love. Philip Anderson wrote. It's called More is Different. More is different. You have more, it's going to be different. And I really recommend, I think it's available on the internet. You can get it. It's really, and what I really love about this article is that at the end, trying to base an analogy for his ideas, he gives a story. Now, whether the story is true or not, who knows? But apparently, he says there's a meeting way back in Paris. Two eminent writers, Hemingway and Fitzgerald, they're sitting in a cafe in Paris, outside in the cafe. They're just having their coffee, and they're just looking at people going by. Just observing. Fitzgerald says to Hemingway, have you ever noticed why rich people behave differently to others? They have a different behavior. So he asked Hemingway. And Hemingway, the reply was, yeah, because they have more money. More is different. So why do I use this as an analogy for what? What we have going on in the world changes. What you can imagine is that social changes, economic changes, changes. And how can you understand this? More. We have more. There are more people. So you cannot expect the system to stay the same if we have more people. The only thing that we can expect is change, right? More is different, okay? Good. More interactions, more people, more interactions. The phenomena that these interactions produce on a sociological scale is different than what 20 years ago, 30 years ago, 50 years ago. More is different, emergent order. Okay, and if you haven't read Anderson's paper, when I recommend it. Gravity. There's something called emergent gravity. This is Berlin. Now, I don't know. I don't work in gravity. I don't know about this. I've spoken with people, and they say, well, you know, in the gravity community, it's not, these ideas are not well accepted, but it's out there. Now, what this says is that gravity emerges as a consequence of position momentum correlation at the quantum level. So what we see as gravity is that, and this is the relation. Okay. Now, what I haven't put it here, but there's another article. What some colleagues have done is that they took some systems for which they had done some calculations, different systems, atoms, bosonic systems, different systems, and they did this, and they came across a result that was very similar to what the gravitational law is. So the idea is out there, you know, that what is gravity? It's the result of position momentum correlation. Okay. So now, after speaking about all these applications, we now full circle come back. I'm a quantum chemist, so we're interested in chemical bonds. So now, the idea is, can we use the tools here that we have information theory to better understand the chemical bond? Chemical bond has been with us very long time now. You all know in the structure of matter, you got covalent bonds, you got ionic bonds, you got metallic bonds. It seems different types of bonds. Okay? Now, what is the basis of all that? I think it's well agreed that the chemical bond is a quantum phenomena. Okay? But how to explain it? This is still open. Okay? Okay? So we've come full circle. And I think with that, I'll end. I want to thank you for your attention, and thank the organizers once again for the invitation. And please, questions.
Does anyone have any questions?
For the talk. I very enjoyed it. My question is, I don't study too much about the Shannon entropy with the wave functions, but I'm trying to think if study the entropy, the Shannon entropy, can help me to correct my wave function, or it's only to give me information about my wave function. Because I'm thinking if it's a new system that I don't have another wave function to compare, we can use it, that entropy, to correct the function?
Thank you for your question. It's a very interesting question. And because of that, I think you have a gift. Okay. Okay. No, yeah, it's a very interesting question. And let me, we first got into this, okay, because chemists, everything is approximate. Well, for most everything is approximate. So you want some kind of measure that will tell you how good your approximation is. Okay? So this is why I think the first studies, okay, you can use the Shannon entropy and you can use the Shannon entropy sum, okay, to tell you how good your approximation is. And this is related to the maximum entropy principle, which states that of all the distributions obeying the restrictions that you have put for the system, you should choose the one with the largest entropy because it's the less biased. Okay, so the idea in the beginning was to use this solo as a tool to understand how good it is, because what you have at the time is the energetic criteria, which was introduced by Levine. Okay, that you can take the exact non-relativistic energy minus the Hartree-Fock energy. This doesn't really matter, right? But it's a difference, and this difference will tell you how good your wave function is, because it will tell you how much electron correlation there is in the system. So in the beginning, it's just been used as something to guide, to tell you, okay, well, I won't use this because it's not very good, okay? But after that, okay, what you can do it is you can use it like how the people use it in Bose-Einstein condensate, to really examine what is the effect, what are the effects of interactions. So it has come from just a tool to understand kind of a technical, how good it is, to really understanding phenomena related with correlation, which is another way of saying this is interaction. How do things interact? In data science, how things interact, you want to feed data into a neural network. Okay, you have what data? Well, you have a sea of data. You have to choose. It's impossible to feed everything in, so you have to choose. So what you try to do is you don't want data that are strongly correlated with other data because it's not going to serve. So in that sense, that you are using this in a different way. Okay, I don't know if that answered your question.
Thank you. Is there any other question? Okay. Yes, please.
Hugo.
First of all, let me congratulate you because it's a wonderful communication in English, of course. This is a joke. My second is a comment that we're using this Wigner function approach in cosmological models. And in regard to the interpretation of the negative values of the Wigner function, in fact, it is possible to see that for certain kind of quantization, that is called the loop quantum gravity, there is no classical singularity at the quantum level, of course, and then this Wigner function becomes negative near the classical singularity. So that's one applications in quantum gravity.
Yeah, no, very good, Hugo. So what is it? This is where, so I would say that this is an affirmative to say that, yeah, the Wigner function, even though it's negative, but there is phenomena, interesting phenomena that is associated with these negative regions of the Wigner function.
And I'm glad that you are a fan of the Wigner function. And I have a question.
Not too many.
Not too many. Okay. Well, anyhow, my question actually is in regard to the collapse of the wave function, whether there is something to say from the point of view of the Shannon entropy or something related to it.
In the collapse of the wave function. Oh, that's a very good question. How you could use the Shannon entropy for the collapse of the wave function, because this is what I was trying to say. I think if I understand this, is that we have the wave function, and in the moment that we choose the representation, we go to X, the X representation, or we go to the P representation, and we are collapsing. So there is a loss of information. So at the moment, to be honest, how one can use the Shannon entropy to look at the process of collapse of the wave function, I would not be able to say about how one can go about because what we have are elements is that it has already collapsed because we are in X or we are in the P representation. Now, how to go back beyond that?
Do we have more questions? Okay. Once again, thank you, Dr. Roy, for your presentation. We have prepared a small gift and a certificate for your participation.
Okay. Thank you, and thank you for your attention, and thank you.